Hello, this is Richard Hammack's Calculus 1 course. We are in part 4 of the course on applications of derivatives. In our previous lecture, lecture 32a, we talked about concavity and how the second derivative of a function tells you its concavity. Today in lecture 32b, we're going to put that to use in what's called the second derivative test. It's an alternative to the first derivative test for finding local extrema, but whereas the first derivative test uses the first derivative, the second derivative test will employ the second derivative. Let's start with the recap of what we know. We know that a function f increases where its derivative is positive and decreases where its derivative is negative. In our previous lecture, we noted that f is concave up, where its second derivative is positive, and f is concave down, where its second derivative is negative. We've also established the first derivative test for finding all the local extrema of a function f. And it works like this. Suppose you've got a critical point of your function f. In other words, that means f prime of c is equal to 0, or f prime of c is not defined. So like one of these values of c indicated here. If f prime goes from positive to negative at c, then f of x has a local maximum of f of c at c. So for example, here the derivative is going from positive to negative. So your function f was increasing, and then at c it started decreasing. And you have, therefore, a high point on your graph, a local maximum of f of c. Secondly, if f prime of x goes from negative to positive at c, as you read from left to right, then f of x has a local minimum of f of c at c. So here we have, for example, right there, f prime going from negative to positive. So your graph stopped decreasing at c and then started increasing. And f of c is a local minimum. And finally, if f prime does not change sign at c, then you can definitely say there is no local extremum at c. And you can see that happening right here, where f prime on one side of this critical point c was positive. It's positive on the other side too, so it didn't change sign. And that just means the graph was increasing and leveled out, had a slope of 0, and continued increasing. That's not a local maximum. So as I said, today's goal is the second derivative test. It's an alternative to the first derivative test. It's going to do exactly the same thing, find local extrema, but it's going to use the second derivative. I'll state the second derivative test at the bottom of this page, but first at the top, I'll explain the simple idea behind it. The second derivative test is a way to figure out your local extrema of your f of x just by looking at the second derivative. Now in the setup of this, suppose c is a critical number of f, or a critical point of f, where f prime of c equals 0. Not undefined, but equals 0. And I'm going to draw you some pictures where we have local max and local min in this setup. And we're going to start with this picture. Right here at x equals c, I've given you a local minimum. That's a possibility. We have a local minimum at x equals c. But look at the shape of that graph. It's concave up. So if it's concave up, its second derivative is positive. So this picture tells us that a positive second derivative signals a local minimum at your critical point. On the other hand, suppose we had a local maximum at c. The picture might look like this. local max at C, and notice that that graph is concave down to give you that local max. So if f is concave down, we know that f double prime of x has to be negative. Interesting. Negative second derivative signals a local max because it means your graph is concave down. It looks like this. These simple observations are the basis of what's called the second derivative test. And I'll give it to you now. Here it is. Now, the second derivative test, it does exactly the same thing that the first derivative test did. It finds local extrema of f of x. It just does it in a different way. And here's what it says. It's got three statements, and the first statement is really going to summarize what happens in this first picture. Suppose C is a critical point of f of x for which f prime of C is equal to 0. And I'm sorry, this is just set up right here. Suppose we're in the situation, this could apply to either this picture or this one, where C is a critical point of f of x for which f prime of C is equal to 0. Now there are going to be three statements about this critical point here, and the first one is going to summarize what's happening in this picture. It says that if f double prime of C is greater than 0, then f of x has a local minimum at C. And we saw that happening here. Here's C, f prime of C is greater than 0, we have a local minimum. The second statement, in words, it's going to say that this picture holds up. It's just going to be a verbal mathematical language for what's happening in this picture. If f double prime of C is less than 0, then f of x has a local maximum at C. And that's here. Local maximum at C, concave down, so f double prime of C is negative, as advertised. Now, finally, what's the third thing that could happen? Well, you might have f double prime of C equals 0. And here's where you really wish the theorem would say, or the test would say, that there's no extrema, or no extremum at C. But unfortunately, things are not so good. If ever f double prime of C equals 0, then there's just no conclusion. And this happens sometimes, not often, but sometimes. And if you're ever in a situation like that, you have to go back and use the first derivative test, which does give you a conclusion. So we're going to look at some examples of the second derivative test. But first I want to say a few things about it. First of all, be careful in what it says. Somehow I always think it's the reverse of what I expect, because if f double prime of C is greater than 0, sometimes I sort of jump to say, well, we're going to have a maximum, but no, it's a minimum. F double prime of C greater than 0 gives you a minimum. And f double prime of C less than 0, that gives you a maximum. This is coming from these pictures. If you ever forget, just draw yourself a picture and you can reconstruct it for yourself. So I've restated the second derivative test up here. I want to emphasize that this test does the same thing. It accomplishes the same goal as the first derivative test. It finds extrema for f of x. And I'll be honest with you, you actually don't need the second derivative test, because this first derivative test will always work, and you can always use the first derivative test. That said, there are some advantages to the second derivative test, and first of all, it can be very easy to use. Very easy. If you think about the first derivative test, you had to do this chart and look at the sign of f prime and see where it changed signs, and that was sort of labor intensive. Second derivative test says, you want to know whether you have a local max or a local min at this critical number? Just pop it into the second derivative and look at whether you get a positive or a negative, and there's your conclusion. And that's simple. There are some disadvantages, and one of them is that this only works for critical points for which f prime of c is equal to 0. And that's part of the setup of the second derivative test. So if ever you had a critical point where f prime of c was not defined, the second derivative test is not going to deal with that. It's not going to. You just can't use the second derivative test. You got to go back and use the first derivative test. And the second drawback of the second derivative test is that it can be inconclusive if ever f double prime of c is equal to 0. Let me say a few words about how it could be inconclusive. I think you can see why you would make the conclusion about a local minimum and a local maximum based on the second derivative being positive or negative in looking at the pictures we saw in the previous slide. But why in the world would there be no conclusion when the second derivative is 0? I hope to convince you that that is the way it should be by giving you 3 examples. And in these 3 examples, first of all, we're going to have a local maximum, we'll have a local minimum, and then we'll have no extrema. And in every single case, you'll see that f double prime of c is equal to 0. So by itself, that means f double prime of c equals 0. Can't tell whether you're going to, it doesn't tell you whether you're going to have a maximum or a minimum, or neither. So in the first picture, here's an f of x. It's f of x equals x to the 4th. It's sort of like a parabola. It crosses the x-axis right at 0. And it clearly has a local minimum at c equals 0. Let's calculate the derivative. F prime of x is 4x cubed. The second derivative is 12x squared. And let's plug in that critical point c equals 0 into the second derivative, and we get 0. So we get f double prime of 0 equals 0. So we're in a situation where we plugged in the critical point, we got 0. Second derivative test says there's no conclusion. And you might look at this picture and you say, well, it means you have a local minimum, right? Because that's what the picture says. But hold on. Here's another example. This time we have a local maximum at c equals 0, and the function is 1 minus x to the 4th. So it's got a y-intercept of a 1 right there, subtracting off x to the 4th. So it's going to be kind of like a parabola that's opening upside down. So you definitely have a local maximum right there at x equals 0. Look at the derivatives. F prime of x is minus 4x cubed. F double prime of x is minus 12x squared. You plug in your critical number 0, f double prime of 0 equals 0. So in these pictures, in both cases, we got f double prime of c equals 0. In the first case, we had a local minimum. In the second case, we had a local maximum. So you see how it's working? If you get 0, you could have either a local max or a local min, depending on what your function is. There's no way to make a real conclusion. And finally, here's a situation, f of x equals x cubed, where there's no extremum at c equals 0. Look at the derivatives. Here's f prime of x, here's f double prime of x, and you'll see that f double prime of x of 0 equals 0, as before. So if you get 0 in your second derivative, depending on the function, it could be no extrema, a maximum, or a minimum. There's just no conclusion. It's all over the map. Let's work a few examples of using the second derivative test to find the extrema of functions. In using the second derivative test for this purpose, just like in the first derivative test, your first step is to find all the critical points of your function f. at least in this case, those for which the derivative equals 0. Then for each one you found, you're going to plug it into the second derivative and see whether you get positive or negative, and base your conclusion on that. Our first example may look a little familiar because we've already solved this problem using the first derivative test a couple of lectures ago, and now we'll use the second derivative test. We want to find the local extrema of the function f of x equals 2x cubed minus 3x squared plus 5 on the entire real line. So the first step here, as always, is to find the critical points of f. And to find them, you have to calculate the first derivative. F prime of x is 6x squared minus 6x. We factor that and set it equal to 0, and you can read off your critical points. X equals 0 and x equals 1. Those are the values that make the derivative 0. Critical points are 0 and 1. Now the next thing we're going to do is plug those into the second derivative. And, of course, first we have to compute that second derivative. F prime is 6x squared minus 6x. So the second derivative is the derivative of that. It's 12x minus 6. So let's take our first critical point, which was 0, and we're going to plug it into f prime prime. F prime prime of 0 is 12 times 0 minus 6, and that's negative 6, which is less than 0. Remember what the second derivative test said? It said if f double prime of your critical point is negative, then you've got a maximum, a local maximum. So that's our conclusion. A local maximum at x equals 0. And that local maximum has a y value. It's f of that x value of 0, which is 5. It's so easy. We're going to move on now to our next critical point, which is 1, and we're going to plug that into the second derivative. F double prime of 1 is 12 times 1 minus 6, and that's positive 6, which is greater than 0. It's positive. And remember what the second derivative test said about this situation. Positive second derivative means local minimum. So we have a local minimum at x equals 1. And that local minimum would be f of that 1, which is 4. So we've got a local minimum of 4 that occurs at x equals 1. And that's it. We've just found our local extrema, just in these 5 lines. The second derivative test can be very simple, as you can see. And real quickly, here's the picture of y equals f of x that we drew when we solved this problem the first time. And you can see you've got a local maximum at 0 and a local minimum at 1. In our next example, we're going to find all the local extrema of the function f of x equals x times e to the x on the interval from negative infinity to infinity, the entire real line. This one may also look familiar because we solved this very same problem already with the first derivative test a couple of lectures ago. The point here is to use the second derivative test, and you'll see that you get exactly the same answer. Whenever you're finding extrema, you have to first of all look for your critical points, because those are the values of x for which the extrema may occur. Finding the critical points means you have to look at the derivative and find out where it's equal to 0 or undefined. So here we got a product, so f prime of x is 1 times e to the x using the product rule plus x times e to the x. Factoring that out, that's e to the x times 1 plus x. Now we want to find the critical point, so we set that equal to 0. Well, the e to the x is always positive no matter what x is, but x equals minus 1 could give you a 0 here in this factor. So we only get one critical point. and it's x equals minus 1. F prime of minus 1 would give us 0. Now, we want to find out whether we have a local max or a local min at x equals minus 1. And the second derivative test says we can figure that out by plugging that into the second derivative and looking at the sign. But first of all, we have to compute the second derivative. Now, let's use this form of the derivative, f prime. We have to compute the derivative of it now. And it's a product, so we use the product rule. So first the derivative of e to the x times your second function 1 plus x plus your function e to the x times the derivative of the second function. The derivative of 1 plus x is just 1. So cleaning that up, we can factor out an e to the x. We get e to the x times 1 plus x plus 1. And that's e to the x times 2 plus x. And I'll put that in the box. That's our second derivative. F double prime of x equals e to the x times 2 plus x. So we need to figure out whether we have a local max or a local min at x equals minus 1. The second derivative test says just plug that into f double prime. Plug in minus 1. You get e to the minus 1 times 2 plus minus 1. E to the minus 1 is 1 over e. 2 plus minus 1 is times 1. And we get 1 over e. And e is positive, so 1 over e is positive. So f double prime of minus 1 is positive. And what does the second derivative test say about that? It says we have a local minimum at x equals minus 1. And there's our answer. F of x has a local minimum at x equals minus 1. Because at that critical point minus 1, the second derivative was positive. Positive means minimum. And there's no local maximum because there was only one critical point, minus 1. We've already considered it. There's a minimum there. If there was a local maximum, it would show up at some other critical point, which we don't have. New example. Let's find all the local extrema of the function f of x equals sine to the fourth x on the interval from minus pi to pi. Now, just sort of to put in your back pocket, I want to emphasize that f of x equals sine to the fourth x it's really f of x equals the function sine of x raised to the power of 4. And I'm writing it that way because in a moment we've got to take its derivative, and it's helpful to remember that that's like a function raised to the power of 4. So you're going to have to use the generalized power rule to find that derivative. Okay, so we're looking for the local extrema of this function on the interval from negative pi to pi. And remember that all of your local extrema, they're going to occur at critical points. The critical points are your candidates for the location of your local extrema. So we got to find those critical points first. And finding the critical points means that you have to find the derivative of f. So here's f of x. We use the generalized power rule. F prime of x would be, let's see, bring down the 4 in front of the sine of x to the power of 4 minus 1. And then you have to multiply that by the derivative of sine of x. And there's your derivative. It's defined for all values of x. The only critical points you're going to pick up are the values of x that make this derivative equal to 0. So we set it equal to 0, and now we're going to solve for x. Now, f prime is already in factored form here. It's 4 sine x cubed times cosine x equals 0. So in order for that to be 0, one of two things has got to happen. Either the sine of x is equal to 0, making that first factor 0, or the cosine of x is equal to 0, making the second factor 0. It's the only way that these two things could multiply up and give you 0. So we have to figure out what values of x are we talking about that make sine of x equal to 0 or cosine x equal to 0. So here x is plugged into a trig function, so you know it's a radian measure. It's on the unit circle. Mind you that x is in the interval, open interval from minus pi to pi. So x is going to be somewhere between negative pi on the unit circle and pi. Neither negative pi nor pi is in the interval that x is in. So x is never going to be equal to negative pi or pi, but just between those two. Let's look at the sign of x equals 0. There's only one value of x between negative pi and pi that makes sign of x equal to 0, and that's x equals 0. So that's a critical point right there. That makes the derivative equal to 0. Now again, sure, sine of pi is equal to 0 too, but you wouldn't include x equals pi because remember pi is not in the interval in question. Then we could also have cosine of x equal to 0. Well, cosine of x is equal to 0 when x is pi over 2 or negative pi over 2. So this gives us three critical points: 0, pi over 2, and negative pi over 2. And what we need to do is find out which of those give us a local maximum or a local minimum. So for this, we could use the second derivative test. And the second derivative test says for each one of these critical points, plug it into the second derivative and see whether you get a positive or a negative. You get positive, you've got a local minimum. If you get negative, you got a local maximum. Well, either way, it involves calculating the second derivative, so let's get to work on that. Here's the first derivative. It's a product, 4 sine x cubed times cosine x. So we got to use a product rule. First of all, we differentiate the 4 sine x cubed. That's a 12 sine x squared times cosine x, using the generalized power rule, multiplied by that second function, cosine of x. And then plus, you do it the other way around. You take your first function, 4 sine x cubed, and you multiply it times the derivative of your second function, and the derivative of this cosine x is minus sine x. Little cleanup here. The cosine x times the cosine x is a cosine squared x. The sine x times the sine x cubed is a sine to the 4th x. We got a negative that we'll bring over there in front of the 4. So f double prime is 12 sine x, sine squared x, cosine squared x, minus 4 sine to the 4th x. Our next step is to start plugging our critical points into the second derivative. Let's start with pi over 2. F double prime of pi over 2 is 12 sine squared pi over 2, cosine squared pi over 2, minus 4 sine to the 4th pi over 2. Now, cosine of pi over 2 is 0, so this whole factor drops out. That's 0. This whole term drops out. And then, let's see, sine of pi over 2 is 1. Raise it to the power of 4. It's 1 times minus 4. You get minus 4. And that's less than 0. And remember what that means? It means you got a local maximum according to the second derivative. So at x equals pi over 2, there's a local maximum for f. Let's move on to the other critical number, the negative pi over 2. Plugging that in, it's much the same computation. Cosine of negative pi over 2 is 0. Sine of minus pi over 2 is negative 1, but then you're raising it to the power of 4. So this turns out to be negative 4 again. Again, it's less than 0. And you've got a local maximum of your function at x equals minus pi over 2 by the second derivative test. So we're cruising along. We have one more critical point to consider. Are we going to get a local max or a local min or neither at that critical point x equals 0? Let's find out. The second derivative test says plug that into the second derivative. You get 12 sine squared 0, cosine squared 0, minus 4 sine to the fourth 0. And, okay, sine of 0 is 0, so this drops out. And this sine of 0 is 0 there, so that drops out. All you get is 0. Now, that's unfortunate. You took f double prime of your critical number, and you got 0. And you were hoping to get less than 0, which would be a maximum, or greater than 0, which would be a minimum. But equal to 0, that's that inconclusive case. So we don't know yet whether we have a local max or a local min at x equals 0. And this is the time, with heavy heart, that you go back and you say to yourself, I've got to use the first derivative test. Okay, you've got to look at f prime of x, which is written up here, and draw a chart and see how its sign changes around x equals 0. And here's my chart here. If you are between negative pi over 2 and 0, that would be x in this fourth quadrant, where sine is negative and cosine is positive. If you work this through here, you're going to get a negative. Whereas on the next interval from 0 to pi over 2, x is in this first quadrant between 0 and pi over 2, and sine and cosine x are both positive, and you get a positive right there. So at 0, you change it from negative to positive, and the first derivative test says you got a local minimum there because you're changing from negative to positive. Now, I'm just for purposes of enlightenment, I've gone ahead and I've drawn the graph of our f of x here, and you've got a local maximum. See, it's increasing, then decreasing, then increasing, then decreasing. You've got a local minimum right there. So we can come back where we were inconclusive. Now we definitely have a local minimum, and we've now answered the question. F of x has a local minimum at x equals 0, and it has a local maximum at x equals minus pi over 2 and positive pi over 2. So when we say we have a local minimum at x equals 0, remember that's telling you where the minimum is. The actual minimum would be f of 0, which is also 0. And likewise here, we have a local maximum at pi over 2. The actual local maximum would be f of pi over 2, which, work that out, would be a 1. So we have a local maximum of 1 at pi over 2, and a local maximum of 1 at negative pi over 2, and a local minimum of 0 at 0. New example. Find all local extrema of f of x equals e to the x minus 2 e to the minus x minus 3x on the interval from negative infinity to infinity. Okay, so whenever you're finding local extrema, you first of all want to find all your critical points, because it's critical points where your extrema will happen. Any extremum is going to happen at a critical point, remember. And finding the critical points involves finding the first derivative. Working this through, the derivative of e to the x is e to the x. Then the derivative of minus 2 e to the minus x is, now that's a chain rule problem right there. It's not e to the x, it's e to the negative 1 times x. So you got to use a chain rule there. Minus 2 e to the negative x times the derivative of negative x, which is 1 minus 3. So f prime of x is e to the x plus 2e to the minus x minus 3. And if you'll allow me to, just because I don't like negative powers, I want to bring this e to the minus x down to the bottom. 2 stays on top because it's not raised to a negative power, just the e to the minus x goes to the bottom. So f prime of x is e to the x plus 2 over e to the x minus 3. Now we're looking for critical points, and those are where the derivative is either 0 or undefined. And e to the x is always defined, it's always positive, so you could plug in any value of x that your heart desired here, and you'd get an answer. So there are no critical points for where the derivative is undefined. But there might be some critical points where the derivative equals to 0. And so to find those critical points, you take f prime of x, which is this we had above, and you set it equal to 0. And you're going to solve that. So that means isolate the x. Now one of the first things you'll notice is that it's problematic. Both of those x's are exponents, and then one of them is way down there in the denominator. Let's at least fix that a little bit. We could multiply both sides of this equation by e to the x. So e to the x times 0, and e to the x times all of this. And multiplying that through, e to the x times e to the x is e to the x squared, e to the x times 2 over e to the x is 2, and e to the x times negative 3 is minus 3 e to the x. And over here, e to the x times 0 is 0. So we need to solve this equation for 0. So solve this equation for x. You have all of this equals to 0. You want to find the values of x for which this is equal to 0. And it looks a little complicated, but let's turn that around a little bit. Let me get the minus 3x first, and I'll put that constant of 2 at the end. If you look at this, it has the form of a quadratic equal to 0. Something squared minus 3 times that something plus 2. It's like y squared minus 3y plus 2. And you can factor that. It factors this way. E to the x minus 1 times e to the x minus 2. Now, if that looks confusing, go ahead and multiply those back in together, FOIL it out. E to the x times e to the x is e to the x squared, minus 2 e to the x, minus 1 e to the x, that's minus 3 e to the x, and negative 1 times negative 2 is positive 2. So we could solve this equation by factoring. You have two factors multiplied together equal to 0. So the only way that that could be 0 is either if this first factor is 0 or if the second factor is 0. And we'll look at those individually. For e to the x minus 1, how could that be equal to 0? Well, such an x would be a critical point. And if you think about it, the only x that works is x equals 0, because you would have e to the 0, which is 1 minus 1, gives you 0. So x equals 0 makes this first factor 0. What about the second factor, e to the x minus 2? How could that be 0? Well, it could only be 0 for those x that make e to the x equal to 2. And what value of x is going to make e to the x equals 2? Well, ln of 2. E to the power of ln of 2 is equal to 2. So that minus 2 is 0. Now, off to the side, just remember, ln 2, that's just a number. It's a number you have to raise e2 to get x. It's approximately 0.69. But at any rate, we have these two critical points, 0 and ln of 2. And so we want to use the second derivative test to figure out whether we have a local maximum or a minimum at x equals 0, and also a local minimum or a maximum at x equals 2, ln 2. So either way, that's going to involve calculating the second derivative. And here, I think the easiest form of the first derivative to differentiate would be this one. So we'll differentiate that term by term. the derivative of e to the x is e to the x. The derivative of 2e to the minus x would be 2e to the minus x times the derivative of minus x, which is minus 1. And that gives you minus 2e to the minus x. And then the derivative of negative 3, that's 0. So there's your second derivative. The second derivative test says that what you're going to do to figure out your local extrema here and there is you're going to plug those x values into the second derivative, one by one. And before we even do that, let me just rewrite this second derivative without the negative exponent, just to make our calculations a little bit easier. And let's start with x equals 0. We're going to plug 0 into f double prime. And we're plugging it into here. So that's e to the 0 minus 2 over e to the 0. And e to the 0 is 1. So this is 1 minus 2. It's equal to minus 1, and that's less than 0. And that means, by the second derivative test, f of x has a local maximum at x equals 0. Now let's next look at ln of 2. We got to plug ln of 2 into f double prime. Plugging it in here, that's e to the ln2 minus 2 over e to the ln2. Well, e to the ln2 equals 2, so this gives us 2 minus 2 over 2, which is 1, and that's greater than 0, which means you have a local minimum at this critical point of ln of 2. And there you go. Our local extrema would be, we have a maximum of f of 0 at x equals 0, and a local minimum of f of ln of 2 at ln of 2. That's it for today. To recap what we know so far, we now have tools for finding local extrema. We can use either the first derivative test or today's second derivative test. In our next lecture, we're going to put this to work to find what are called absolute extrema. And the idea here is that with local maximum, say, you could have a number of local maxima for a function. We're going to begin to look at what values of x give you the absolute highest f of x value you could possibly have, or the lowest f of x value. That's next time with absolute extrema. I'll see you then. Goodbye.